All right, we're going to get started at 5:05 Pacific time, which is in about 2 minutes. So just hang tight. All right, let's get started. So, hi everybody. Today is week 8 of our class, which is the topic is going to be polynomials 2. So last week we covered polynomials 1, which was things like linear equations and defining polynomials of general degree. Remember that the degree of a polynomial is the highest exponent of x, or whatever variable the polynomial is in. So we sort of introduced that, talked about linear equations, and we briefly covered the relations between roots of polynomials and their coefficients. So remember that a root of a polynomial is a value for which when you plug it into the polynomial, you get 0. So the roots turn out to be really important. Um, the roots turn out to be really important a function of polynomials. Um, and we're going to get started today by the agenda for today is to cover things like Vieta's formulas, which are a very key relation between the roots of a polynomial and the coefficients of a polynomial, um, and surrounding theory related to Vieta's formulas. So let's first recap what we remember about roots and coefficients of a polynomial. So in case you don't remember what those are, so remember a polynomial, let's just go through it from the beginning, can be defined by its coefficients, which are basically, so you can define by its roots or its coefficients. The first way, which I'm going to mention, is by coefficients. So you learn that a polynomial is, say, 3x squared plus 2x plus 7, or x squared minus 7. Um, and that's basically telling you the coefficients of each of the powers of x. So the coefficient of x squared I'm telling you is in 3x squared plus 5x plus 7, say. The coefficient of x squared I'm telling you is 3. The coefficient of x I'm telling you is 5. And the constant coefficient, which we call the constant term, is 7. So one way to define the polynomial is if I tell you its coefficients, and then you can write it in the way I mentioned. Using, if the coefficients are a sub n minus 1 all the way to a sub 0, then p of x is a sub n times x to the n all the way till summed till a1 times x plus a0. So that's the that's sort of the initial definition of polynomials. That's 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 how they're defined, and we say this is by the coefficients because you're given each of the coefficients of the powers. So now the key thing here is that we can also define it using the roots. Any polynomial of degree n. So remember, a polynomial which has highest exponent n, we say has degree n. So another way to describe a polynomial is by its roots. And remember that a polynomial with degree n has exactly n roots. So like I said, there's n roots. Let's call them r sub 1 through r sub n. Then in fact, the polynomial, we can write it, it'll have a leading coefficient, but the point is we can write it as some leading coefficient times x minus r sub 1 times x minus r sub 2 all the way till x minus r sub n. Now this might be a little confusing, so let me back up. Basically what I'm saying is there's two ways to define a polynomial. And you can think about it as the coefficients or by the roots. So I can tell you that a polynomial is 3 times x minus 2 times x minus 5. Obviously, you can expand that to get the coefficients, but what I'm saying is that the roots turn out, the way to define a polynomial with its roots turns out to be really important as well. So this
So,
is, yeah, go
oh
ahead.
yeah, another thing that's really important is these roots R1 to Rn. You can't just say they're real numbers. For instance, the polynomial x squared plus 1 doesn't have any real roots, so you can't factor it like a factor it with real numbers only. You have to say 1 times x plus I times x minus I.
Yeah. So what Alan is mentioning, if you've heard of complex numbers, that the roots in general can be complex numbers. So, for example, the polynomial x squared plus 1 doesn't have real roots. So
It's
anyways,
x plus I times x minus I, the root roots.
exactly. Yeah. So I and negative I are not real. So this is one way, this is another way to describe a polynomial. And these are going to be really important because it allows us to determine relations between the coefficients and roots. Now, sort of intuitively, why does this definition make sense? Well, remember, a root of a polynomial is a number when you plug it in, you get 0. So when I plug in r sub 1 into this polynomial, into p of x, I should get 0. That's the definition of a root. P of r sub 1 or r sub 2 or anything should be 0. And indeed, when you plug in r1, then you'll get this r1 minus r1 term here, which will go to 0. So the entire product will become 0. So this sort of makes sense. If I told you the roots were r1 through rn, then that makes sense according to this polynomial, because whenever I plug those in, it gives 0. And why is this leading coefficient here? Well, if I change this to say, like, instead of a equals 1, if I change it to a equals 2, well, then even when I plug in x equals r1, x equals r2, and so on, the product will still be 0. So this is a sort of degree of freedom that we can't control. It can be anything um, that we want, and this polynomial will still satisfy the fact that p of r sub 1 is 0, p of r sub 2 is 0, and so on, no matter what this leading coefficient is. So this is another way to describe polynomials. This relation is going to be very important. All right. Now, the question arises, how can we relate the roots and coefficients of a polynomial? That's why we're introducing this entire concept. So it is difficult to find the coefficients of a polynomial if you are only given the roots. And the way to do that would be using expansion. So if I told you the roots of the polynomial were 2 and 3, then it would be of this form, a times x minus 2 times x minus 3. And then you could expand that to find the coefficients, using any method of expansion you like, you can get the coefficients. Um, Another thing that's very hard is, given the roots of the polynomial, it's difficult to find the roots of a polynomial given only the coefficients. So that's what we call factoring. If you have a polynomial, say x squared plus 7x plus 5, there are ways to find its roots, but that is also hard. So what we're going to introduce is, what we're going to talk about is, how can we relate the roots and the coefficients. All right, and now this is just an example. The polynomial x plus 2 times x plus 3 is 0, has roots -2 and -3, and it can also be expanded as x squared plus 5x plus 6. So there are two ways to, the key point is that there are two ways to represent any polynomial, by its roots or by its coefficients. Now, Vieta's formulas, these are something you might have heard about. Which is the main focus of today. This is all sort of set up for that. Why are Vieta's formulas important? And they basically allow us to find relationships between the roots and the coefficients. Specifically, if we're given the coefficients, we can find the sum of the roots, we can find the product of the roots, and we can find other things about the roots. It's hard to find the roots just directly. That requires factoring, but Vieta's formulas are a way to find relations between the roots given the coefficients, which we're going to talk about. So before we get into Vieta's, Alan is going to go through an example about roots in polynomials. So I'm going to stop sharing. Alan, I think you're muted. I don't know if you're talking, but
Whoops, sorry about that. So we have a polynomial p with integer coefficients, and note that it's called a tricky. This is for the problem, if it has 4 as a root. And a polynomial is called teeny if it has degree that is at most 1, and all its coefficients are between that's supposed to be -7 and 7. So how many non-zero tricky teeny polynomials are there?
So take a few minutes to try this problem. Again, the 7, it should be -7 to 7. And then we're going to go through how to do it. So make sure you have some pencil and paper, and there's some way you can get to work on this problem. And we're going to come back in about 5 minutes. Yeah, again, somebody's asking if you found out the answer or if you have any questions about the example, feel free to direct message either myself or Alan. So All right, we're gonna take about another 1 or 2 minutes, and then we'll go over how to do it. All right, let's go through how to do it. Again, if you're still working on the problem, then feel free to keep working, and we're gonna go through the solution, which you can view at a later time. But Alan,
All
let's go
right,
through how to do it.
so we have we have a degree zero. If we have a degree zero polynomial with 4 as a root, then it's gotta be the constant zero polynomial, because you can't really have a root of, say, 3.5 equals 0, much less 4 as a root. The only function that's actually true for x equals 4 is just 0 equals 0. And we have a restriction that our polynomial has to be non-zero. So that can't work.
Alan, someone's asking, can you define a degree zero polynomial? Just
Okay,
in
so
self-contained.
all right, a degree 0 polynomial is a constant polynomial because the maximum exponent on x is a times x to the 0, or just a. So what this means is that we can only talk about polynomials of degree 1. So if if p has degree 1 and has 4 as a root, then we have to have it in the form a times x minus 4 for some integer a, non-zero, since we have a non-zero polynomial. So all of our integer coefficients have to be between -7 and 7, though. So what this means is that a -7 must be less than 4a, which in turn must be less than 7, which means we only have 2 possible values for a, -1 and 1. That means that that works because our coefficient for the constant part is between -7 and 7 here. This means that since there are 2a, there are going to be 2 of these polynomials.
Yeah. Again, if you could go back one slide, Alan.
All right.
The 7 between 4a
Wait,
7 should be a -7.
Yeah.
Yeah, but go ahead. All right. Yeah. So. All right. Yeah. So thank you. Go ahead, Alan.
Oh, did Shori have a question?
Actually, my name is Akshaj.
Oh,
By
sorry.
the way, if a degree is, I didn't get the first part. Like, if a degree zero polynomial has 4 as a root.
Oh, so the key thing is our polynomial has to have a degree of at most 1. In addition to being ax plus b, it could be just b as a degree 0 polynomial.
Right. So I think the question would be that for a degree zero polynomial, what are its roots? So like Alan said, a degree zero polynomial is simply a constant function. If you think of polynomials as functions, then a polynomial of degree zero is just going to be a function that outputs the same number no matter what you plug in. Now the question is, when can this be 0? Well, if it ever outputs 0, if it ever has a root, and if it ever outputs 0, that means the entire function must be 0, because we know no matter what we plug in, you have 0. So a degree 0 polynomial, it only has a root if the constant function is always 0. So that sort of clarifies why what we mean when we say the root of a degree 0 polynomial. So yeah, this example should hopefully solidify or sort of help clarify concepts about roots. The main step, like Alan said, was if it has 4 as a root, then you can write it as a times x minus 4 for some a.
We'll be seeing that structure a lot more this session.
Yeah. So should I share yeah, go ahead with the next example, Alan. So now we're going to transition into more Vieta formulas setup.
So we're going to do an example with the roots for Vieta's formulas. So first question, can you find a degree 2 polynomial that has roots of 2 and 3? Take maybe 30 seconds to try this.
All right, I'm getting a lot of responses.
Okay, so it turns out that any polynomial that we can get in the form a times x minus 2 times x minus 3 has roots like this. And as people have noticed, this can also be just x squared minus 5x plus 6. But it's notable that we have that a as well. You can't ever forget that you sometimes have to multiply by that constant. All right, so this one, we're taking into account that coefficient. What degree 3 polynomial has roots 2, 3, and 5, and has a leading coefficient of 100? Just leading coefficient is that coefficient on our highest term, the x cubed term.
Yeah, just to ask any questions or submit your answer, just direct message either myself or Alan. And there's no need to expand this in your notebook or whatever. Just type in what it should be.
How did you get 67?
Oh, that's just a random value of a, basically.
All right, I'm also getting some responses. So.
Yeah, okay. All right, so our answer is going to be 100 times x minus 2 times x minus 3 times x minus 5. This is because our a has to be 100 in order to get that 100x cubed, and we have to have x minus 2 for root of 2, x minus 3 for our root of 3, and x minus 5 for our root of 5. All right, now we're going to see how this sort of thing helps us with doing Vieta's formulas. Is Ram going to share this, or should I?
Yeah, do you want to stop sharing?
Okay.
All right, so like Alan said, these were just some examples to make sure you understand in sort of concrete terms the relation between, if I just tell you what the roots are, can you write down the polynomial as a product of some terms? So now Vieta's formulas, like I said, it's going to relate the roots of a polynomial to the coefficients. So let's do an example. So let's say I start off with the coefficients sort of definition of a polynomial. Let's say I tell you that the polynomial is 2x cubed minus 7x squared plus 100x minus 73. Again, these are just randomly chosen numbers. So the point is this doesn't factor very nicely at all. You won't be able to factor it just using integers or possibly even real numbers. So, but let's say I just want to find the sum of the roots. So obviously if I told you to just find the roots, that would be pretty hard. You'd have to factor in some way that might involve complex numbers or other stuff. But let's say I just want to find the sum. Is there an easy way to do that? So I want to find the sum of the roots. Let's define what the roots are. Let's say the roots are r sub 1, r sub 2, and r sub 3. Again, there's 3 roots because it's a degree 3 polynomial. That's an important fact. So what can we say? If the roots are r1, r2, and r3, well, we know that p of x is 2 times x minus r1 times x minus r2 times x minus r3. And again, the reason the 2 is there is because we know in p the leading coefficient is a 2. So we can just say that it's 2 times x minus r sub 1 times x minus r sub 2 times x minus r sub 3. And we want to find r1 plus r2 plus r3. So what can we do with this? Well, the only thing we can really do with this is the key point of Vieta's formulas. If you haven't been listening so far, make sure you're just understanding the main point, which is that there were 2 definitions for polynomials using coefficients and using the roots. The key of Vieta's formulas is to expand the definition from the roots that you have. So we have this definition right here. We know what p is in terms of the roots. We can expand this and then relate it to the coefficients sort of definition of the polynomial, and then we can get relations between the roots and the coefficients. So the key is to expand this. Now, this is sort of a daunting task. I mean, there's x minus r1, x minus r2, x minus r3. So you might not be comfortable with expanding this directly, but I'll go over that next. The sort of, if you want to think about how do I multiply this out, again, we're expanding. So instead of trying to maybe expand this times this first, then multiply in this, a really good way to think about this is, can I just find the coefficient of x cubed when I expand this out? So you're going to have an x, and so you can think about about expansion as you basically are choosing one term from there's an x, there's a negative r1, there's an x, there's a negative r2, there's an x and a negative r3, and in each term in the expansion you're going to have one term from this term, one from the second term, and one from the third term. So you can say the coefficient of x cubed, the only way you can get x cubed is by doing x, x, and x. If I do x negative r1 and negative r2, then I'm not going to have 3 x's. So the coefficient of x cubed, and I'm going to multiply by 2 at the end. So that's not very important. The coefficient of x cubed is simply 1. For x squared, well, how can I choose 2 x's and then a constant number? So constant would be things like r1, r2, and r3. Well, I can do x, x, and negative r3. And again, as I'm saying, this is sort of just a way to think about expansion. Obviously, if you're familiar with expansion in a different way, you can confirm at the end what I claim it's going to be to sort of convince yourself. But what I'm explaining is a sort of a very efficient way to expand these kind of polynomials. So again, the coefficient of x squared, how can you get an x squared from this? You can have an x, you can choose an x, and a negative r3. You can choose an x, a negative r2, and another x. And basically what I'm doing here is I'm saying, how can I get 2 x's and then something else? So what you're going to have is x squared times negative r3 plus x squared times negative r1 plus x squared times negative r2. So the coefficient of x squared will be negative r1 minus r2 minus r3. And you can keep going on like this. And eventually what you're going to get is that, obviously I'm keeping the 2 out, you're going to have x cubed. So again, this is just purely expansion. There's nothing too tricky going on here. All I'm explaining is a efficient way to expand. If you expand this out right here, what you're going to get is x cubed minus r1 plus r2 plus r3 times x squared plus r1 r2 plus r2 r3 plus r3 r1. So those are all the combination of 2 r's times x, and then minus r1 r2 r3. Now you might notice that the signs are alternating. You have plus x squared minus plus and minus, and the reason for that, if you go back to the way I was talking about in terms of choosing, By the way, the negative you should really think about as an x plus negative r1. So that's the minus sign might be a little confusing, but it's just x plus negative r1. And in order to get the constant for the constant term of the polynomial, for example, you have to choose negative r1 times negative r2 times negative r3 in the x plus negative r1 times x plus negative r2 plus x times negative r3 expansion. And that's why we have a minus r1, r2, r3. So that's just an example of why this sort of expansion makes sense. Now, going back to the key point, how can we come up with the roots, the sum of the roots of the polynomial? Well, you can see it sort of floating around here, but what we can say is that the coefficient of x squared in P of x is negative 2 times r1 plus r2 plus r3. So again, the 2 comes in and the coefficient of x squared is simply this. Now going back, we already knew that P of x has coefficient negative 7 for x squared. So r1 plus r2 plus r3 is negative 7 halves. So that's how we found the sum of the roots of this polynomial. And again, we only did it by the coefficients. So let me just recap. We started off with P of x in terms of its coefficients, and then we expanded out the roots definition, and then the sum of the roots popped up, and we only had to go back to the coefficients to find what is the coefficient of x squared, because we know it's minus 2 times r1 plus r2 plus r3, but we also know it is, again, this should be negative 7. So that's why that works out. Now we generalize this method to any degree n polynomial. So if r1 all the way till r sub n are the roots of a polynomial, p of x is a sub n times x to the n. So I'm just writing out the coefficients expansion. And then we also have the roots expansion. So the roots in this case would be r sub 1, r sub 2, all the way till r sub n. And the leading coefficient is still a sub n. The question is, if I expand this out, I can find relations between the roots and plug that back. We already know what all the coefficients are. So we can get relations between the roots and the coefficients. Now, I'm not going to go through the exact expansion, but let's just do the first couple terms. I'm going to keep the a sub n out of it. When I expand this, what I'm going to have is an x to the n. You know, if you have n terms, then you're going to have an x to the n. What's the x to the n minus 1 coefficient? Well, you can have x to the n minus 1 times negative r1, x to the n minus 1 times negative r2. Now, again, if the sort of way I was explaining how you expand didn't really make sense, this might not make perfect sense right now, but you can trust that this is when you expand this, when you expand x minus r sub 1 all the way till x minus r sub n out, you're going to get something like this. You're going to have a minus r1 plus all the way till rn as the coefficient of x to the n minus 1. And the coefficients in the middle kind of get a little nasty, but the constant coefficient is negative 1 to the n times r1 all the way till rn. So now the main point was to plug it back because we already know what all the coefficients are and we can relate. So the coefficient of x to the n minus 1 in the roots expansion is negative an times r1 plus all the way till plus rn, but we know it's a sub n minus 1, and therefore we have r sub 1 plus r sub 2 all the way till r sub n is negative a sub n minus 1 over an. This is a really, really important formula. Don't just memorize it. It's important to see where it comes from, which is why we were explaining. But the key is that if you sort of just treat all this as a black box, you don't really get what's going on here. Or if you don't want to just sort of trying to remember this formula, what you have is p of x is a sub n times x to the n plus a sub n minus 1 times x to the n minus 1, and so on. Then the sum of the roots is negative a sub n minus 1 over a sub n. And similarly, if you expand the x to the n minus 2 term, you're going to get another relation, which is between the product of any two ri's when you sum that up. Then it's going to be a sub n minus 2 over a sub n. I'm not going to go through exact details, but if this sort of method makes sense, then you should, you might believe this. And so on till the product of the roots is r1, r2, all the way till rn. And then we're going to have a negative 1 to the n times the a0 over an. Now, this might look like a lot of symbols, but let me just break down the key parts. The sum of the roots and the product of the roots, remember, can be found easily just using the coefficients of the polynomial. That's the main point. And r1, r2, all the way till rn. So you do negative 1 to the n. So that's basically the parity of n. If it's even or odd, then it flips. And then you do a0 divided by a sub n. So this might look like a lot of symbols right now. So let's break it down using a few examples. And Alan, you want to take over?
All right, sounds good.
Actually, I'll just mention one more thing once Alan starts sharing his screen, if that's okay.
Right, so
Could I just mention one thing, Alan? I forgot.
yeah, sure.
Could you go back to the previous slide?
Yeah.
So one way I remember these formulas personally, for the sum and the product. So for the sum, it's basically you have a sub n x to the n plus a sub n minus 1 x to the n minus 1 and so on. So you just take the first two coefficients and then you do negative the second one divided by the first one. All right. So basically the key point is to sort of parse all these symbols and see what's really going on. The sum of the roots is negative the second coefficient over the first coefficient. And similarly, the product of the roots is negative 1 to the n, so that if n is even, that's positive. If n is odd, that's negative 1. And then the final coefficient divided by the first coefficient. So when I say final, I mean constant, and then divide by leading. So the key point is to sort of parse all these phrasings, all these methods. And we're just going to actually, why don't we just hold this slide here for about a minute to, if people just want to make sure they understand or just write these down, the sum of the roots and the product of the roots, and then we can go on to the next slide, which has the
Yeah,
example.
these are some pretty important formulas, notably.
Again, the really important ones are the sum of the roots, r1 plus
Yeah.
r2 all the way till rn, and r1 times r2 all the way till rn. So just make sure you like note those down or sort of understand what's going on there, and then we can move on to a couple examples. So let's just pause for about 30 seconds.
All right, on to the examples, if you have those written down. Okay, so what is the sum of the roots of 2x cubed plus 3x squared plus 7x minus 3?
I haven't gotten too many responses yet, so maybe let's hold off for a minute. Again, feel free to direct message myself or Alan. All right, I've got a couple of responses. You want to explain it, Alan? You're muted, I think, if you're speaking.
Okay, yeah, it turns out it is negative 3/2. Sorry if I said that wrong. I was looking at the product of the roots, and that's because we have the negation of 3 divided by our first formula, 2. And that's our answer for this one. Next one, what is the product of the roots of this equation?
All right, I've got a couple
Yeah.
responses.
Okay, so the product of the roots we get as -4 over 3, and that's going to be equal to -4/3. Last one divided by first one. Okay, next question. What is the sum of all the products of pairs of roots in 3x cubed minus 3x squared minus 2x plus 4? This is one of those lesser known formulas.
Yeah, we actually didn't go over this, so
Oh,
it
it's all right if you.
turns out to be, yeah. Actually, go ahead, Alan. But yeah, this is one of those formulas, like Alan said, which isn't as important, but it's important to know that you can find the sum of the pairs of products of the roots. That's sort of the, yeah. All right, I've got one response. Maybe you just want to go to the quadratic one, Alan.
All right, yeah. So it turns out that this one is -2/3. We have this -2 over 3, but this is an edge case, and you might not need to know this. But here's a more general one, which is very, very useful. What is the sum of and product of the roots in the general quadratic ax squared plus bx plus c? Just say it in terms of a, b, and c.
All right, I've got most responses. You want to go through it, Alan?
All right. So our answers are -b over a and c over a. because we have the negation of this one over this one and this one over this one. Now, I got quite a few responses that accidentally put negative signs or skipped the negative signs on one of these. This is a really easy place to mess up on a lot of tests. So make sure to remember where those go. You can't always derive it from what Rom showed earlier of using a factorization with roots to derive it.
And one thing just for the quadratic case, you can also derive the negative b over a and c over a using just using the quadratic formula, which you may be familiar with. But the point is we can get around that really easily in the quadratic case. But you can confirm it just to check that it works.
All right. Now we're going to go on to an example from an AMC 10. We have all the roots of this polynomial are positive integers. So what's the value of b?
Yeah, this was actually on this year's AMC 10A, so maybe if you guys took that, it might be familiar. But yeah, it's pretty applicable to what we're talking about. So take a few minutes and then we'll go through it. I think let's come back at 5:55, and then you can explain it, and then we can wrap it up.
Right. Right. This is a really difficult question, especially to solve into in a time limit. So don't feel bad if you can't get it.
All right. Actually, Alan, you want to go through right now? Again, it's hard to
All
get
right.
within the
Yeah.
time limit, but since we're running short on time.
Right. Yeah. So by Vietta's formulas, we can find that that the sum of the roots is the negation of -10/1, which is 10, and our product of the roots is 16/1 or 16. So actually the first step in this problem is to try to find some roots that satisfy this. Turns out the best way to do this is probably through trial and error. But you can find that the roots are 2, 2, 2, 2, 1, and 1. You can get this by looking at groups of 6 numbers that multiply to 16 and finding the ones that sum to 10, basically. All right, so we have our factorization of the polynomial. If we can just expand this, we can find out what our z cubed term is. That's what b is. So you could expand this using the binomial theorem and multiply those, or you could use Vietta's formula as a more complicated version with more than sum and product of roots. But in any case, you should find that your answer is going to be -88.
All right. I think since we're running short on time, thank you for the explanation.
Yeah. Oh,
Alan.
one more
Yeah,
thing.
go ahead. Sorry.
If you want to know what that more complex thing was and what those sums of pairs of roots, products of pairs of roots, you can probably go to resources like AOPS Wiki. It's a pretty good resource for things like that.
Yeah, just in general, anything on Vietta's formulas, which has a bit more time than we did, should go through the sort of
Yeah.
other identities that sometimes come up, as well as other problems related to it. Anything else, Alan, or should I just
I
go to
don't
announcements?
think so, no.
All right, yeah. So we're going to publish the handout, which is we didn't publish it last week because the handout for this week and last week is going to be the same. That'll be published soon to the website, and there you can have extra practice problems to work on. And so that concludes today's class. Thank you, everybody. But just stay for a couple minutes because this is going to be our last class for the winter spring session. And we're going to continue next academic year, which is going to be around September of 2021. And stay tuned for notifications, any email updates we're going to send. But yeah, everybody, thank you for attending. We might send a survey or something like that just to see how this sort of went for everybody. But yeah, we'll get the handout published and the recordings, and we're going to restart next academic year in about September. So thank you everybody for attending
Thank you so
so
much
far,
for coming.
and we'll see you later.
Did we have a question?
Thank you.
Thanks for the
Thank you.
I have a question.
Yeah.
Sure.
What about the geometric one?
Geometric what? Sorry.
The geometric class, you publish it on the schedule.
Oh, yeah, we're gonna when we restart, we're gonna probably start with geometry.
Okay.
The schedule has changed. You can find the updated schedule on the website, and that has been postponed to whenever we restart. So stay tuned for whenever we start. It's gonna come on your email and everything.
Okay.
All right.
All right, I'm gonna end the meeting.
So
now.
what's the restarting time again?
You're gonna get an email update whenever we restart.
Okay, thank you for coming, everybody.